Welcome to this course on the foundations of continuum mechanics. Today we'll be talking about viscous type of models in constitutive modeling. So let us get started. So let us answer a question first as to what a fluid is. A fluid is a material which cannot resist shear stress in equilibrium. So if you apply a shear or a shear stress to a fluid, it definitely will flow. It may resist it, but it will still flow. It cannot stay in equilibrium under a shear stress. And in comparison to our elastic type of solid models, in a fluid, the stress depends on a rate of deformation, not strain. Rate of deformation is the same as rate of strain. But before we present to you the actual constitutive model for a fluid, let us look at the stress for a fluid. So the stress tensor sigma has a spherical part and a deviatoric part. So tau is the deviatoric part, which basically is called the shear stress. So the constitutive models for fluids typically are written using shear stress, not the overall stress. Now the word shear stress is a bit misleading because technically it is the deviatoric part of the stress, and shear stress sigma s, as we've been talking about, has a different exact meaning. But in general, we call this tau ij in fluids as the shear stress tensor more commonly. So for solids in general, the stress sigma, it depends on the strain epsilon, as we saw last time in the elastic laws, whereas for fluid, our sigma depends on the rate of strain or the rate of deformation d. So d here is our symmetric part of the velocity gradient tensor. So here we present to you the constitutive law for a Newtonian fluid. Now let's define what a Newtonian fluid means. So a Newtonian fluid means it's linear, that is the constitutive model will be linear. Then it is isotropic, so that's a special case where you have an isotropic material. And as we discussed that in fluids, we talk about relating tau with d. So the deviatoric part of the stress is related to the rate of strain or the rate of deformation in fluids. And the reason is because in fluids, when you apply a shear stress, the fluid starts to flow or continuously keep straining. And since we're talking about a linear situation with isotropic material, so the law exactly is the same as we had for linear isotropic elastic solids. So you have two constants, mu and lambda v, which are similar to the Lamé constants we had for solids. And these constants are called the shear viscosity, and the lambda v is called the bulk viscosity. So these coefficients are the viscosities for the fluid. Now for most practical situation working with fluids, the Stokes hypothesis is valid, and we'll discuss this in detail next week when we talk about fluids in detail. Then the bulk viscosity is given as minus 2/3 of the dynamic viscosity mu. So in that case, we are left with only one viscosity coefficient, that is mu, which is called the shear or the dynamic viscosity. Now here's a clear comparison of a linear isotropic solid with a linear isotropic fluid, also known as Newtonian fluid. So we see that in solids, we relate sigma with epsilon, and in liquids, we relate the deviatoric part of stress, that is tau, with the rate of deformation tensor, that is d. So we called lambda and mu as the Lamé constants, and in this case we call mu as the shear viscosity and lambda v as the bulk viscosity. Now basically in solids you have a rate independent response, that is your stress or the response depends on epsilon, not the rate of change of epsilon. So time does not play a role here, it is the instantaneous effects that matter. Whereas for fluids, we have a rate dependent response, that is our tau, the response, is dependent on the rate of strain, that is, the time rate change of the strain. But in a sense, mathematically speaking, both of these are linear and isotropic, and therefore they have only two material constants to characterize them. But there's also a fundamental difference energy-wise between solids and fluids. Now, elastic solids, for example, they store energy. When you perform some mechanical work, that mechanical work gets stored as strain energy in the material. And that allowed us to define the W potential function. But in fluids, they are dissipative. And if you apply some shear stress, for example, to a fluid, it will dissipate that energy through its viscosity. So energy-wise, they are very different materials. Now, usually when dealing with water and air, a Newtonian model suffices. But there are situations where the fluid may not be linear or it may not be isotropic. So in those situations, the Newtonian model is not valid. And there are many fluids, real fluids, which deviate from this model. So in that case, you may require a different model, and such models that are not Newtonian are called non-Newtonian fluid constitutive models. So Newtonian law basically is a very special case which provides a linear relationship between tau and d, and it is for isotropic fluids. So for something to not be Newtonian, it could be a non-linear fluid, still isotropic but non-linear. So that is the coefficients, in this case viscosity coefficients, they depend on the shear rate or the strain rate, or they include something called a yield stress, and we'll talk about this soon. Some examples of non-linear isotropic fluids could be paint, blood, or dense slurries, which are typically found in mining operations. So in these materials, we see a shear thinning or shear thickening response, that is, the viscosity tends to change with the rate of strain or the shear. And there are materials such as mud where you have a yield stress. So what that means is that these materials tend to behave like a solid until the shear stress increases beyond a certain yield value, and then they become fluids. Non-Newtonian fluids also include fluids where the viscosity is time dependent, that is, it evolves with sustained shear. So these include materials such as clay suspensions or gypsum paste, where the viscosity changes with time when a shear stress is continuously applied to them. Then we have a class of very interesting fluid which are called viscoelastic fluids. So they show both an elastic solid-like behavior and viscous, which is a fluid-like behavior. And we'll be discussing these in a little bit of a detail today. And these materials include polymers, molten plastics, even bread dough. So typically, the first two classes, that is, nonlinear isotropic fluids and time-dependent fluids, typically are isotropic. And then viscoelastic fluids may or may not be isotropic. Again, they can be linear or nonlinear. But then we have anisotropic fluids, which is very interesting because typically fluids are well mixed. So we expect isotropy in the rheology of a fluid. However, there are some fluids which may include liquid crystals or fibers suspended in a fluid continuum. These fluids have a microstructure orientation, and that results in a directional preference or anisotropy in the viscosity of the fluid. So the overall message is that non-Newtonian basically means departure from the linear isotropic constitutive model for a typical fluid. So now we'll talk about a couple of non-Newtonian models which are typically used for modeling non-Newtonian fluids in different situations. So the first one, which is a very popular model, called the power law fluids. And again, these are nonlinear isotropic fluids we're talking about. So experimentally, we see that some fluids do not have a constant viscosity. That is, their stress and rate of strain or shear rate are not linear, they are nonlinear. And as we saw from representation theorem that the coefficients of a constitutive model or a constitutive tensor should be functions of invariants of the cause. In this case, the cause is our rate of deformation tensor. So to quantify the nonlinearity, in this case, we have to define an invariant to work with. So the invariant we work with is called gamma dot effective or the effective shear rate. And that's given as the square root of twice dij. Actually, for an incompressible fluid, this turns out to be the J2 of D. The J2 was the second invariant of the deviatoric part of D, as we had discussed earlier when talking about octahedral shear stresses. So we usually use J2 or gamma dot effective to quantify nonlinearity in power law fluids or nonlinear isotropic fluids. So this basically allows us an invariant or just one unique quantity that we can calculate from the rate of deformation tensor, and that helps us specify the viscosity of the fluid. So if gamma dot effective increases, then the viscosity could increase or decrease depending on the behavior of the material, but we could quantify the viscosity as a function of gamma dot effective. So J2 is a useful invariant to collapse a complete 3D tensor into one single scalar. And similarly, we also define something called an equivalent stress, which is again an invariant tau ij times tau ij. So let's demonstrate the tensor form of an isotropic power law fluid, which is also incompressible. So tau ij is twice of k, where k is some constant, times gamma dot effective to the power of n minus 1 times dij. Now when you write the definition of gamma dot effective, it becomes this form. Now, as discussed in the representation theorem, our tau is a function of d with the coefficient depending on the invariants of d. In this case, just one invariant of d. So as we saw that for this incompressible case, our dkk term is missing. So we only have this form, and that is quite common because mostly the fluids that we talk about to be modeled using power law are incompressible in nature. And we can clearly see it's a nonlinear model because the effective viscosity, as we see from here, is dependent on gamma dot, which contains information about D. So now that we understand this model, let's see which fluids fit this category. So if I put n equal to 1 in this equation, I clearly see that the gamma dot effective effects in the viscosity goes away because n minus 1 is 0. So tau ij is simply dependent on dij and the viscosity is a constant. So if we draw a plot between equivalent shear stress and gamma dot effective, then a Newtonian fluid would be a straight line because the viscosity, which is the slope here, is a constant. And then there are materials which are shear thinning, that is n is less than 1. So as the shear rate or the rate of strain, or in this case the effective shear rate, decreases, then the shear stress required to sustain that also decreases. So materials or fluids like ketchup, blood or paint, they're usually shear thinning. So they'll show a behavior which looks like this. And then if you look at shear thickening materials, where n is greater than 1, what that means is that as you try to increase the rate of strain or the effective shear rate, then the shear stress required, effort required is increasing. So these are the materials which show this kind of a behavior over rate of strain. These are n greater than 1 and these are n less than 1. So power law fluids are very popular and typically used to model fluids which show either a shear thickening or a shear thinning behavior. We also have fluids which are called Bingham fluids or Bingham plastics sometimes. These are also again non-Newtonian fluids, but these fluids have or show a solid-like behavior until the shear stress increases beyond a threshold value. So let's look at the plot first and then we look at the equations. So this is the plot between shear stress tau and the shear rate gamma dot. So we can see that we would expect a Newtonian fluid to show a straight line like we have here, the black dashed line, but a Bingham plastic or a Bingham fluid will have a very steep response in the beginning, which basically means that if we keep increasing the shear stress, there is no flow or no rate of strain, and then all of a sudden, beyond the threshold value, also known as the yield stress, the material starts to behave like a fluid. So tensorially, we see that if the equivalent tau is less than a yield stress value, the rate of deformation is 0. It behaves like a solid. There's no continuous rate of strain. And then if the equivalent stress increases beyond the threshold value of yield stress, then the material starts showing a fluid-like behavior. And the examples of Bingham fluids are toothpaste. You may have noticed that when you try to squeeze the toothpaste out, in the beginning, nothing happens, and then all of a sudden it starts squeezing out like a fluid. So when I say in the beginning nothing happens, you may see an elastic kind of a behavior like a solid, where if you release the stress, this toothpaste may go back in. Other examples are mayonnaise, some drilling muds, and also debris flows in nature. So until the shear stress goes or exceeds beyond a threshold value, the debris stays there, and beyond that, it starts flowing like a fluid, like a very thick viscous fluid. And now we can combine the behavior of yielding fluids, the Bingham plastics we just talked about, which show this response of a very steep solid-like behavior and then flowing like a fluid. But we combine the Bingham fluids with power law fluid behavior. So what that basically means is that we may have a shear thickening or a shear thinning behavior along with the yielding behavior in a Bingham fluid. So these fluids, which combine the idea of yielding and nonlinearity, are called Herschel-Bulkley fluids. So in 1D, it shows a yielding stress and a power law kind of a behavior with an index n. Typical examples of this are granular avalanches, where there is some cohesive yield stress. So the water along with the granular material like snow particles, for example, may provide some sort of a cohesion due to the surface tension effects, and that results in a yielding behavior. But then in snow avalanches, we see shear thinning behavior. So we have an n less than 1 beyond the yielding. So avalanches, mud flows, and cement pastes, which is basically collection of some solid particles in a fluid continuum, show this Herschel-Bulkley behavior. And then we have many other models which are very specialized. For example, I talk about this cross model, which is important for us because we work with modeling of snow avalanches. So here in this case, we notice that the viscosity mu changes with gamma dot like this. So for very low or zero rate of strains or effective shear rate, we see that the viscosity is mu naught. which is typically happening when the microstructure, because you have solids in a fluid, the microstructure is intact, but when the strain rate increases, then the microstructure breaks and we can have asymptotically an infinite shear viscosity mu infinity. So this sort of lets us interpolate between a zero shear viscosity and an infinite shear viscosity. And then we can have parameters which allow us to control the transition and sharpness and so on. So summarizing whatever we have discussed till now, we need an invariant which was J2 of D, that is the second invariant of the deviatoric part of the rate of deformation tensor D, and using that we can quantify the nonlinearity in the model, such as we did in power law models, Bingham or Herschel-Bulkley models, and even in cross models. Now moving on to other non-Newtonian fluids, we have a class of fluids called time-dependent fluids. So for these fluids, under constant shear or shear stress, the viscosity evolves with time. So if you have a shear stress or a shear strain being applied to a fluid, you would see that the viscosity will change with time. So this is different from the models that we discussed just now, because in those models, we noticed that the viscosity was a function of effective shear or shear strain. But here, for the same shear strain, the viscosity may change with time. So examples are thixotropic fluids, where the viscosity decreases with time. So the fluid becomes easier to flow with time. And there are rheopectic fluids where the viscosity increases with time. That is, with time, the fluid becomes difficult to flow. So since the viscosity mu is changing with time, so we define a model for mu dot, which could be a function of mu and also could be a function of gamma dot. Now moving on further, we have two phenomena. One is called creep and the other is called stress relaxation, that is typical of fluids which are called viscoelastic fluids. So before we discuss viscoelastic behavior, let us talk about these phenomena and understand what exactly they are. So creep is a phenomena where experimentally, let us say you provide a constant stress sigma naught and then you observe what happens to the material in terms of the strain in the material with time. Now let us say the material was purely elastic solid. Then what will happen is, as soon as you provide a sigma naught, you will see an epsilon which is sigma naught upon E, so which is based on the Hookean solid. So we see an instantaneous strain develop and the strain is constant, which is equal to sigma naught upon the Young's modulus of the material. Now if you are applying the same experiment onto a viscous fluid, then what will happen is, if you apply a sigma naught onto a fluid, the material starts to flow. That is, you have an epsilon which linearly increases with time. So this is an unbounded growth of strain for fluids. But in the case of viscoelastic fluids, which show both the viscous and the elastic behavior, there's a combination here. So let's plot and see what happens. So in this test, we have a constant stress sigma naught and we are measuring the strain over time. So what we'll see is that for these viscoelastic fluids, there's an instant jump in the strain. There is a solid behavior. So all of a sudden, a strain develops. And then because it also has a fluid-like behavior, so it starts to linearly increase its epsilon with time. So this is a viscoelastic fluid where we see that there's a gradual creep over time. That is, if you're looking at the material with a constant sigma naught, the material starts to creep or elongate gradually, unboundedly over time. But actually what happens is, for these viscoelastic materials, we notice that there's no unbounded strain. Strain gradually becomes or asymptotes towards a constant value. So this behavior of a strain developing suddenly like a solid, and then gradually the material expanding or straining over time or creeping over time is called creep. And then we can have a dual of creep, which is known as stress relaxation. So in this testing, what we do is we apply a constant strain. So you take a material and stretch it along a certain direction and hold it. So you apply a constant strain epsilon naught to a material. And then you observe sigma as a function of time, that is a stress required to hold the material in the constant strain situation. So let's plot and see how sigma will evolve over time. So if I'm talking about a solid, a purely elastic solid, what I notice is that sigma is some constant, that's Young modulus times epsilon naught. So the sigma develops suddenly. Now if you're talking about a purely viscous fluid, then sigma will tend to zero immediately. So if you take water and try to pull water, there's no sigma required at all. But for viscoelastic fluids, which show both a solid and fluid-like behavior, what we see is that when you apply an immediate strain, the material develops a stress and then it starts to relax over time. So that means to hold the same strain, the material now is becoming fluid-like. So we see the stress gradually decreases and asymptotes towards a zero. But since we're talking about actual fluids, what happens is that this asymptote does not asymptote to a zero, but to a constant sigma. So creep and stress relaxation are two important phenomena that indicate a viscoelastic behavior in a material. So let's talk about linear viscoelasticity now using spring and Dashpot models. So as we said, it's the elastic or the spring-like response where the stress depends on the strain or the instantaneous strain, and the viscous or the Dashpot-like behavior where the stress or the shear stress depends on the rate of strain, bringing in the memory effects in the material. This combined behavior of a viscous and an elastic type of behavior is called viscoelasticity. And then coming to the modeling of these, they are typically captured by using spring and Dashpot models. So we briefly talked about the Maxwell and the Kelvin-Voigt models in the beginning of this module. So in a Maxwell model, we have a spring in series with a Dashpot, and when we apply a stress, the stress equally goes to the two elements, but the two elements have different strains. So there's a strain in the spring and there's a strain in the Dashpot, and the overall strain is a sum of epsilon s and epsilon d. And using the model of a spring, we can say that sigma is E times epsilon s, and for the model of a Dashpot, we can say sigma is eta times epsilon d dot. So if I take the derivative of the first equation as well, and along with that I take a derivative of this strain balance as well, so I get epsilon dot as sigma dot upon E plus sigma upon eta. And this is exactly the same as what we have given here. So this is the ordinary differential equation for solving for sigma in this case. So the example of materials which are modeled using the Maxwell series model are polymer melts, cheese, and asphalt. The other type is called the Kelvin-Voigt model, typically used to model rubber or biological tissues. So Kelvin-Voigt configuration is when you have the spring and the Dashpot in parallel. So that means that they share the same strain, but the stress is different. So this will have a sigma spring and this will have a sigma dashpot. So the equation becomes overall sigma is sigma s plus sigma d, and sigma s is E times epsilon and sigma d is eta times epsilon dot. So we get the same equation that we have here. And then we also have a model which is actually quite useful for modeling both creep and relaxation, and that's called a standard linear solid or SLS model. So this model is a parallel combination of a Maxwell model, which is basically like this, along with a spring element. So I'll not write the equation for this. We'll do that as a tutorial problem later this week. But this is the configuration of a standard linear solid model. And you can come up with lots of models like the Maxwell branches we talked about in the beginning of this module as well. So let us talk a bit more about the creep phenomena. So creep, as we discussed, was when you apply a constant stress on the body and measure the strain in the body. And we saw that in creep behavior in realistic viscoelastic materials, we see that there's an instantaneous elastic jump in the strain, and then eventually the material creeps or plateaus to a constant strain value. A classical example of this is asphalt, where when you apply a stress, it behaves like a spring, but then eventually it creeps and a constant strain persists. Now the question is, which model do we use for this? So we have to try different models. So if we try a Maxwell model, so as in the Maxwell model, it keeps elongating or straining, which is unrealistic. Then if we try the Kelvin-Voigt model, then if you look at the behavior, the solution to this equation, we see that it gradually approaches to sigma naught upon E, but we don't see this initial solid-like behavior in the Kelvin-Voigt model. Because if you put t equal to 0 here in this equation, for epsilon, you see that epsilon is 0. And this is where our standard linear solid model shines, because it shows both the instantaneous jump in strain and the retarded creep that is asymptoting to a finite value of strain. So the SLS model provides the best match for creep scenario. Now let's also talk about stress relaxation, where you provide a constant strain to a body and measure or observe the stress as a function of time. So typically for such viscoelastic materials which show relaxation behavior, the stress initially is high, like a solid-like stress develops in the body, and then it decays over time to a non-zero plateau. And typical examples are biological soft tissues. So again, trying out different models. If we try the Maxwell model, we get this response of stress. So at t equal to 0, we get a sigma naught, which is what we expect, like a sudden stress developing. But from this decay response, it decays to 0. But if I look at my standard linear solid model again, then what we see is that it shows an exponential decay as expected, but to a non-zero plateau. In this model, we see that it plateaus to a non-zero stress as expected. Now, rather than performing a creep and a relaxation test separately on a material, what we do is we perform an oscillatory test. That is, we oscillate the strain sinusoidally like this. So that's still a strain control test. And this reveals both the elastic storage and the viscous dissipation response in one test. So the solution comes out to be like this for sigma, where G prime is called the storage modulus, which helps us understand the elastic behavior, and G double prime is called the loss modulus, which helps us characterize the viscous behavior of the material. We'll not discuss this in a lot of detail because discussion on viscoelasticity can be a full course in itself. Now, this form of the behavior of the response for sigma that we're discussing here, it is not dependent on a choice of model. So, for example, if I choose a Maxwell model, I will get a specific form for G prime and G double prime. If I choose another model like SLS, I may get a different form for G prime and G double prime in this expression for sigma as a function of t for this oscillatory test. So if the model was more solid-like, I would see that G prime would be much larger than G double prime. And if the model was more liquid-like or fluid-like, I would see that my G double prime, which is the loss modulus, would dominate over G prime. So the final topic for today's discussion is the integral formulation, which is basically related to the viscoelastic response of materials. So we talked about creep, relaxation, and oscillatory tests, but the solution for sigma that we get fits a standard expression as shown here. Because what we notice is that the stress in viscoelastic materials depends not just on the current strain, but on the complete history of the strain. So this is like a fading memory effect where the strains from previous times, they contribute less as compared to strains from the recent times. So this is called the Boltzmann superposition principle, where we write sigma as an integral of epsilon dot with a convolution kernel or the green function, which is also called a relaxation function. So the nature of this function will quantify the relaxation or the memory fading effect or the contribution of strains from the past times. So again, this is a general expression of the behavior of sigma as a function of time for viscoelastic materials. Different choices of models such as Maxwell, Kelvin-Voigt or standard linear solid models will result in different expressions for this green function or the relaxation function G. So the key idea, which is very important here, is that this is the most general way to express our sigma for linear viscoelastic materials. So whatever models we have discussed in linear viscoelastic materials will result in a response like this. So let's take an example. For a Maxwell model, for example, we see that the behavior is such that the green function or the relaxation function is capital E times e to the power of minus t by tau, where tau is called the relaxation time or the time constant. So here's a quick concept check slide for you. So please try out these problems. They're based on today's lecture. And finally, summarizing today's lecture, we started our discussion with the definition of the behavior of fluids, where we said that solids respond to strain, whereas fluids respond to the rate of strain. Then we talked about linear isotropic fluids called Newtonian fluids, and we showed this linear isotropic law for fluids. Then we had a discussion on non-Newtonian fluids, where we talked about the power law, Bingham, Herschel-Bulkley, cross models, and time-dependent viscosity models such as thixotropic and rheopectic fluids. Then we spent some time on viscoelastic fluids, where we showed that we can combine spring and dashpot models to demonstrate the very interesting creep and stress relaxation behavior that is typically seen in linear viscoelastic fluids. Finally, we briefly mentioned about the integral formulation that allows us to write the historical effects in viscoelastic fluids using a relaxation kernel G, which may take different form for different model choices. So this brings us to the end of the lecture on viscous constitutive models. In the next lecture, we'll briefly talk about plastic models and then solve some problems related to constitutive modeling. Thank you very much, and I will see you in the next lecture.